Okay, welcome everyone to the day 8 of the summer school. I'll share my screen now because I have a couple of introduction slides. Let's see. Can you see my screen?
Yes.
Yes, okay, cool. All right, so let's start. It's day 8 of the CCAI summer school. It's AI for energy systems today. First, we would like to thank our sponsors. So we're supported by CIFAR, by Mila, by Volkswagen Group of America, and by Worldsphere.ai. As you know, probably now that it's we're in the middle of the summer school. So CCAI is a global nonprofit, and we're trying to catalyze work between machine learning and climate change. And we have this. We have our website, we have a community platform, you can see also newsletter. So there's many ways to interact with us. Please try to do it, and we will be very happy to interact with you as well. At the end, it's a community platform as well, so you're very welcome to do so. For this lecture, you can ask questions on our community platform. So I will just mark it here. So we have this lecture Q&A in the community platform. Maybe not all questions will be asked. It depends on the number of questions that we will receive. So don't hesitate to just write your questions, and then we can also probably answer them later. Just to remind you that you're required to abide by CCAI's code of conduct as well. This is the schedule for today. So we will start, it will be divided into 2 parts. We will have a break in the middle. We have 2 speakers today. I'll just present them right now. And this is how it looks. So it's just 2 hours lecture. There are 2 A's in this session. So one of them is me. I'm Jorge Montalvo, and also Samuel Fernandez is in the call. So if you have some technical issues, please write on the chat or try to reach us. Finally, let me introduce you to your lecturers for today. So Priya is an incoming assistant professor at MIT. She's the co-founder and executive director of Climate Change AI. Her research focuses on using physics-informed machine learning for forecasting and optimization in high renewables power grids, and she has received prestigious awards for her work, including the MIT Technology Reviews 35 Innovation 35 and the ACM SIG Energy Doctoral Dissertation Award. And Nsutezo is an applied research scientist, level 2 at Microsoft AI for Good Research Lab. Her expertise lies in computer vision, remote sensing, and machine learning, which she applies to address societal challenges in climate change, food security, and humanitarian crisis. During her PhD at Columbia, she developed deep learning techniques using electricity consumption data and remote sensing imagery to infer electricity demand. And she also holds a master's degree from Stanford University and has worked as a research scientist at IBM Research Africa Lab in Nairobi. So that was the quick introduction, and I'll give you the stuff to Priya and Nsutezo. Stop my sharing.
Good morning, everyone. So just give me a moment to share my screen. Hello, everyone. As Jorge mentioned, I'm Nsutezo Simone, and today Priya and myself will be giving the MLFO Power and Energy Systems lecture. So to start off our lecture, it's worthwhile going through the session goals, One, we want to describe what mitigation, adaptation, and sustainable development strategies for energy and power systems looks like, describe how electric power systems work, share opportunities and considerations for ML in the power and energy system space, provide and discuss some concrete examples, case studies where ML has been applied to power and energy systems, and then provide some context around how to responsibly frame and scope problems within this space. We also want to end this lecture with some potential entry points and next steps for people who are interested. So again, just to briefly go over the outline for this lecture, we'll quickly talk about the importance of power and energy systems, strategies for mitigation, adaptation, and sustainable development within this domain, how electric power systems work, an overview of ML applications, a select set of case studies that Priya and myself will go through, and then opportunities for involvement. So starting off with importance of power and energy systems. In 2019, 34% of total anthropogenic greenhouse gas emissions was attributed to the energy supply sector. And the energy supply sector consists of all infrastructure equipment used to extract, transform, transport, transmit, and convert energy to provide energy services. This includes electric power systems, fuel supply systems, be it natural gas, cooking fuels, and heating and cooling networks. Over the past decade, we consistently see increased emissions in the energy sector. And though there was a brief dip due to COVID-19 in 2020, we see that this has rebounded and is consistent even up until 2021, which is not necessarily shown in this figure. To go into a bit of depth as to which sectors or which sectors within the energy system space are greenhouse gas contributors, we see here that the electricity and heating sector or space is the largest contributor, contributing over 70% as of 2018, and that has grown over the years. Now, looking at low carbon sources given emissions, we notice that within the electricity space, low carbon sources make up only about a third of the electricity space in terms of contributing to electricity. And when we look at the total energy bucket that consists of electricity, transport, heating, low carbon sources are even smaller, making up only about 15% of that space. So given the backdrop of increasing greenhouse gas emissions and the minority role that low carbon energy sources still play, it is important for us to consider what climate adaptation looks like in energy systems and why it is important. So currently, energy systems domain or infrastructure is faced with increasing pressure from climate change. And that consists of increasing in the number and intensity and variability of climate events that do affect energy systems. A large proportion of energy systems are exposed to these climate-related events. This can consist of distribution systems, which are substations and other equipment necessary for energy supply. There's also the effect of shifting demand patterns due to climate change, for example, changes in heating and cooling, which puts increased pressure on the current systems. We are also observing that there's a transitioning in the energy systems space that's shifting to low carbon sources. And these low carbon sources bring along different climate-related vulnerabilities, which need to be considered as we design these systems. Finally, with regions that are still expanding their energy infrastructure, they're faced with a growing population and need to expand infrastructure to meet access, reliability, and high demand, even in places with high climate risk. So all of these factors continue to emphasize why climate adaptation in the energy space is important. For a bit more context around the last point, energy systems are quite important for development. And here we show the Human Development Index as a function of per capita electricity consumption. What stands out here is that there are no countries with a low HDI score that are high electricity consumers. And this suggests that there is that linkage between human development and the amount of available energy within a country. So as we consider strategies for mitigation and adaptation, we need to also ensure that we preserve opportunities for development within different countries. To buttress the point here, again, we show some two countries specifically, Vietnam and South Korea, and look at how energy per capita has evolved given GNI per capita. And we see that as the GNI has grown for these countries, so has the energy usage. Again, suggesting that there is this tie between development, between income and the available energy within a country. So in light of that, we also want to emphasize the need for sustainable development with respect to climate change in the energy system space. And what that would look like for different countries differs, but it's still worthwhile considering. So for more industrialized economies, that might mean reducing greenhouse gas emissions while maintaining levels of development, specifically on the right, moving from the red circles, moving from the top right of the graph to the bottom green corridor. And for emerging economies, that might mean increasing levels of development while maintaining or reducing greenhouse gas emissions, specifically moving the blue circles, moving from the left of the figure to the right end of the figure. So we've briefly talked about why power energy systems are important, and now we want to consider what the strategies would be for mitigation, adaptation, and sustainable development. So we'll take a quick poll right now. Hopefully Jorge can help us summarize some of the takeaways, but briefly drop your answers in the Google Forms. What you think are some strategies to decarbonize energy systems? And Jorge, feel free to highlight a few prior to us moving on.
Sure. Waiting for responses now.
Okay, maybe this is just a warm-up task poll. But Jorge, if no answers are popping up, that's fine. There's no right or wrong answers, just to stimulate conversation. So we'll get into it right now. So for a few strategies to decarbonize energy systems, what is important to note is that net zero energy systems will share common characteristics, but how net zero would look like for every country will differ depending on the localized circumstances within the country. But to help us think about how to address climate change within the energy system space, we find that the CCAI identity presents an interesting framework for the drivers of greenhouse gas emissions. And these drivers consist of population, the service per population, which could be the GDP per capita, the energy service, which is the energy intensity, and then the greenhouse gas emissions given some unit of energy, which is the carbon intensity. So ideally, we want to be able to reduce energy consumption in general, given that one observation is that areas with high, if I may say, GDP also consume a lot of energy. So one strategy might be to reduce energy consumption. The other strategy would be to improve energy efficiency. And then the third one would be switching to clean energy, which will address these individual drivers. The good thing about this framework is that it provides a good linkage between supply side, which is around the types of energy sources that are being used or sought out for generation, and the demand side, which is population and how it's going to be used by the population, either through transportation, buildings, or not.
May I interrupt 1 second, because I see some responses now?
Yes, please go ahead.
On this slide, I think most of the responses talk about the third part, so switching to clean energy. I see some responses that talk about switching to alternative energies or renewable energy like solar and wind power, or use of fuels that are not as that don't emit that much as fossil fuels.
Yes. Those are great responses, and actually flow into the next point, which is that the common characteristics for decarbonization would be electricity systems that are producing net negative or net zero CO2 emissions, and that can come from shifting to low carbon or renewable sources for electricity generation. So very well highlighted in the poll. Electrifying end uses that would include cooking, space heating, transportation, reducing fossil fuel usage, electrifying or using low carbon alternative fuels for hard to electrify loads like heavy duty vehicles, improving energy efficiency or efficiency of energy use, integrating energy systems so that there's more interconnection across regions and across components, and then overall leveraging CO2 removal techniques to offset some of the residual emissions. So great responses in the polls overall. Now that we've briefly highlighted decarbonization strategies, it's again going back to the poll. If you could drop your thoughts, your answers on what some strategies would be to adapt energy systems to climate change. And I'll give that a few minutes here also. Jorge, sorry.
Sorry, I was muted. I said that there is a bit of delay, I think, because it's zero, but they will start popping up, I think.
Okay, great. That's okay. I might give it maybe one more minute before I hop into it. Okay, so in terms of adaptation, one of the things that first comes to the table, if I may say, is being able to accommodate extreme events through fostering robustness and resilience. So that means accommodating correlated failures that may be as a result of extreme weather, and also putting in place methods or approaches to be able to quickly recover given an extreme weather event. How we present this is more of a feedback approach where given an extreme weather event, having in place procedures, methods to be able to absorb shock while operating, being able to manage the disruption as it unfolds, being able to get back to normal service as quickly as possible, then taking away key lessons which can be folded in to prepare for subsequent extreme events. The other aspect in terms of adaptation would be accommodating changes in energy supply and demand. So we expect that with changes in weather, there will be changes in the amount of energy that can be produced, e.g. through solar or wind, and also the demand will change, either heating or cooling demand, so being able to accommodate that quickly. And then finally, being able to build adaptive capacity, so increasing energy access, connectivity, reliability, the amount of energy that people can consume, such that they can be productive and have economic growth while still being able to adapt to climate change in this new environment.
I interrupt 1 second. So most of the responses, they talk about technology. So I guess like on the second point on accommodating changing energy supply and demand patterns. Mm-hmm. So I see some responses on decentralized like energy control, flexible demand response, new infrastructure for renewable energy systems.
Mm-hmm. Yeah, okay. Great responses in the chat. And they sort of align with the general message here, which is being able to accommodate changing energy supply and demand. And interestingly, we'll go into a bit more detail about demand response on and off grid systems slightly later in the lecture. Okay. Moving on to sustainable development and energy systems. Again, making sure that the approaches that are being implemented, the solutions that are being put in place are able to support universal access to modern energy. That means improved, like I mentioned, connectivity, but not just a binary connectivity or not connected, but also reliability and the amount that people can consume for productive use, because that's really where you can support economic growth and economic development, given some amount of supply. Increased reliance on clean fuels, expanding infrastructure, and upgrading dilapidated infrastructure that may be in place, and also the technology that gets the data to be able to make informed decisions. Finally, increasing the share of renewables, like we've mentioned, and low carbon energy sources in the global energy mix, both on-grid and off-grid, depending on what's most suited for the region, and then decreasing energy waste or the energy intensity. So we've gone briefly through some general strategies for mitigation, adaptation, and sustainable development. And now we'll move on to how an electric power system actually works. But I'm going to stop my screen share, and Priya, if you don't mind hopping in right now.
Awesome. So yeah, thanks, Nsutezo. So true to form, we're going to start this off with another poll. So before I tell you what I think electric power systems are, I'd love for everyone to answer in the poll, what is an electric power system? So I'm going to just pause for a minute or so to hopefully give some folks a chance to respond.
Every second feels like super long, but still
I'm
zero.
sure everyone's taking some time to type answers, which is great.
All right, cool. We have a few.
Awesome.
Okay. talking about infrastructure that you can generate, distribute, and balance electricity over a large area of population. Power plants are an example of electricity supply, and then on the other side, the distribution to consumers. System made out of people and technology, which aims to provide reliable and affordable electricity.
Yeah, those are fantastic responses. So kudos to whoever put those in. And yeah, exactly. So when we think about an electric power system, we're thinking about the system through which our electricity is first, generated, and then transported along lines and electrical equipment through our transmission and distribution systems, before then being consumed by end-use consumers like us. And to think about this system, I mean, one kind of useful analogy is potentially thinking about kind of roadways. So when we drive from one place to another, often we'll end up driving on highways to go a very, far distance very quickly, before then kind of exiting the highway and then going on a kind of more local road a little more slowly, but in a way that allows us to get that last mile or last few miles to where we want to go. So the electricity system can be thought of this way too, where we have first power that's produced, it then goes along transmission lines at high voltages, so very efficiently, very fast at far distances, but in a way that wouldn't necessarily be safe if somebody were actually to interact with that equipment. And then we have distribution infrastructure, which transports electricity at a lower voltage in a way that's slightly less efficient, but allows it to be transported a little more safely for that last mile. So this is how our electricity systems roughly work. Now, while on the previous slide, I talked a bit about kind of this idea of, generation to transmission to distribution to consumption, it turns out our electricity systems are changing very quickly, and they're increasingly becoming, less one way. They're becoming more bidirectional, and they're also becoming less centralized. There's actually much more participation, for example, from consumers in actually shaping how the electricity system works. So, for example, when I say bidirectional, what I mean is that before you would have big power plants producing power and that would go one way to consumers. Now what you're starting to see is many more consumers who have, for example, rooftop solar panels that are kind of sending power back up the grid, or batteries that are participating in the electricity system. And so now you have power kind of being put in multiple points in the system and also being consumed in multiple points in the system. So that's what we mean when we say bidirectional flows of power. We also increasingly have non-centralized control of the power grid. So again, historically, what you would have is some centralized power system operator kind of dictating, how much power should each power generator produce. And then that would just be sent to consumers who are very passive and just consuming that power. Now what we start to see is that as we have, for example, more solar and wind on the power grid whose output is varying, we need to actually have consumers who are flexible to be able to respond to that. And so we have notions like demand response, which basically means that those who are demanding power or who are consuming power can be asked to change exactly when they're using power in order to then help deal with the needs of the grid. For example, if there's less power available. And there's also now, with more batteries and more distributed devices like solar panels that have kind of inverters hooked up to them, which are basically managing how that power flows into the grid, you have many more things on the grid that you can control. And there are kind of two main paradigms for how this goes forward. One is called distributed control, which is where you still have somebody in a central position telling different devices how they should act, but then those devices then act based on that. And then you also have a notion called decentralized control, which is that the decentralized devices are themselves figuring out how to act, and then that causes some behavior on the overall system. So distributed is basically someone central telling everybody, all these distributed devices, how to behave, and decentralized is all of these devices choosing how to behave themselves, maybe based on things like prices, electricity prices that they're seeing on the grid. And then so far, I've talked a lot about, a big centralized grid being how it works, but actually depending on where you are in the world or even within any country, within any geographic context, there are actually lots of different ways that grids look. So for example, you have often smaller grids or microgrids that might be completely separated from a main grid, or that might be partially connected to a main grid. You also have homes with personal power sources that might not be connected to any grid, but that might be just completely powered themselves. And we see in islands and rural areas and in various different places at universities that sometimes you see this combination of some centralized grids in some places, microgrids in some places, personal power sources in some places. The grid can basically look very different in different places. But regardless of these differences between grids in different places, there are various, operational constraints that have to be satisfied on power grids. So on a power grid, we need to make sure that at any point in time, the amount of supply or the amount of production that's being put into the grid is basically exactly equal to the amount of power that's being consumed. And in addition, there are lots of different physical constraints that need to be satisfied. So when power is flowing along the lines of the power grid, for example, we need to make sure that we're not overloading any line on the power grid, because otherwise it can't deliver the power that we're wanting it to. And in reality, this is, a tricky, complicated system, but there are some, equations that we can write down to try to conceptualize what's going on at a high level. And that allows us to get some grounding to then try to figure out how to deal with all of the complications that come with this. So specifically, there's a problem that is formulated on power grids called AC optimal power flow, which is just an optimization problem, so a mathematical problem that tries to describe what is actually happening on a power grid when power is being put in. So the goal that AC optimal power flow describes is that you have a centralized power system operator that is setting the power and voltages at all of the different controllable power generators on your system. And the goal is that you generate power in order to try to meet the amount of power that's being consumed. So that both means actually power that's being consumed, as well as the kind of, dealing with the fact that since there's also going to be distributed power generation like solar panels at the consumers that is offsetting some of that consumption, basically what is the remaining consumption that needs to be met. We also hope to minimize power costs, and we also hope to satisfy various grid and operational constraints. And so the AC optimal power flow problem looks like this. And again, this maybe looks big and ugly, but what's going on is exactly what's in the text at the top of the slide, where there's some objective. We're trying to minimize the cost of power delivery or power production. There are various constraints that are captured that talk about, the relationships between different electrical quantities on the grid, as well as the fact that, for example, power generators have a limit on how much power they can produce. So that's all captured here, though there are limits on how much power each line can handle. And then there's also this last constraint called the power flow constraint, which basically talks about, just physically when you put power into the grid, how does it flow along the grid? And this constraint, for those who know optimization, is nonlinear and non-convex, and that makes this overall AC optimal power flow problem, computationally expensive and complicated to solve, even though it is really fundamental. And so actually in the tutorial that'll be released later today, you'll work with different machine learning techniques that are being used to actually approximate this AC optimal power flow problem to try to make it more computationally efficient, and as a result, help it be used more effectively on power grids. Now, for those who really know optimization and have heard of this concept of duality, then one kind of interesting tidbit here is that the dual variable on this power flow constraint actually provides the power prices at different parts on the power grid. For those who don't know about, duality and optimization, that's not an issue at all, but just sort of a tidbit, basically, that this optimization problem kind of implicitly spits out what the power prices are on the grid as well. Okay, so I've given a bit of an idealized notion of, what, how a power grid works and this idea of AC optimal power flow, but I've hinted at the fact that operating a power grid is actually much more complicated than that. And so I'd love to give a minute for everyone to submit in the poll, what are some ways in which operating a power system might be more complicated than what I've described? And here I'm going to give 30 seconds for folks to just write. I'm going to then go on to the next slide, and then Jorge, feel free to interrupt me on the next slide if you see kind of common themes emerging between the answers and the,
Sure.
yeah. Okay, but first I'm going to pause and give everyone some time to write.
I can already give you a couple.
Okay, go for it.
So we have security constraints. So what happens if a component fails? We have uncertainty. So based on weather conditions, demand may be super high and supply is low, and sometimes in the year, like in winter, for example. We have maintenance, redundancy, failures. Yeah, more stuff about weather, like how it influences the power system, like the uncertainty.
Yeah, those are great responses. I'm definitely getting at a lot of the points on this next slide. So amazing. So one thing I mentioned earlier is that since this AC optimal power flow problem is expensive to solve, power system operators will often use some cheap approximations to this problem in reality, and then make some real-time adjustments in practice to deal with the kind of inaccuracies that leads to. The AC optimal power flow problem that I talked about is actually a one-time step problem. So at one point in time, what should happen on the power system? But actually on a power system, of course, you're operating it over multiple points in time. And so, and there are dependencies. For example, if a generator is off during one time step, it can't turn on immediately in the next time step. It takes some time. So there are some problems like unit commitment that deal with this problem over time and encapsulates things like ramp rates. How much can a power generator change its output from one moment to the next? Now, this next one is one of the things that was reflected in the answers. So great job to whoever said that. Uncertainties. So when I presented the AC optimal power flow problem before, I assumed that I knew exactly what the electricity demand would be or what the solar power production, for example, would be. But these are, not perfectly predictable. And that means that in practice, we're often making some kind of estimate of what we think those will be, making some decisions based on that, and then making real-time corrections through mechanisms like automatic generation control to deal with any mismatches between our prediction and the reality. Somebody mentioned security constrained optimal power flow. So this idea that you think that your power generators and your lines are all going to be up all the time, but they might not be, right? They might be out in an unexpected way. And so there's a problem called security constrained optimal power flow that tries to schedule power to be robust to these kinds of outages. There are lots of kind of dynamics that happen on the power grid. So this is a subtle point, but in the AC optimal power flow formulation, really what that deals with is you put power into the grid, and in steady physical state, how is it going to flow in the grid? But there are lots of kind of more minute physics that happen depending on how the power is changing. And this dynamic, these power system dynamics are starting to become more and more of a consideration as we have more variable renewables on the grid whose output is changing in various ways. Power pricing is another kind of complication. So I mentioned this idea that the power prices can be read from the AC optimal power flow problem on the previous slide, but those are the kind of wholesale or true power prices. When I personally pay for power, I'm paying not for a wholesale price, I'm paying for a retail price. And I'm not paying for often a price that's changing over time, I'm paying for something that's more steady. So the fact that different people face different prices leads to different complications. And also a lot of power, even with industrial consumers, is procured ahead of time through something called power purchase agreements, big contracts, which further complicate the pricing question. And in addition, because there are lots of, things that we want to make sure there are lots of power generators on the grid to provide backup if something goes wrong, but then those power generators might not be on most of the time, so they're not getting paid for energy, so they might not be profitable. There are all sorts of payments that happen outside of the power market, things like uplift payments, or they're completely separate markets called capacity markets, which basically pay for attributes like the existence of a power generator that might not be fully incentivized when actually just paying for the power that is produced. So lots of complications like this that make it, all the more exciting to deal with power grids. And there's one more, which is that in some regions, the retail prices are actually very heavily subsidized in ways that actually cause money to be lost when power is delivered to certain consumers. So this happens, for example, in countries where you have very remote agricultural consumers who need power in order to help with the agriculture of the country. But because the power is being delivered such a long distance, a lot of it is being lost along the lines. So it's very expensive to deliver that power, but then consumers get subsidies for it. So they're actually paying less than it costs to deliver to them. And so this actually sometimes causes power system operators in some of these regions, like in India, to not deliver power all the time, not because that power is not available, but because financially they have to figure out how much money they're willing to lose on sending that power over. So lots of different complications with power pricing that are really important to take into account when shaping a power system. And last but not least, when thinking about power systems, you also, of course, want to think not just about the technical system, but the sort of social and regulatory system, like who is actually managing the system. In particular, power grids are natural monopolies, which basically just means that it's really hard to have two sets of power infrastructure in the same place. So whoever manages the infrastructure is sort of naturally controlling what is happening with that infrastructure. And as a result, in many places, this infrastructure is managed either by a public or governmental entity, or by a private entity that is tightly regulated by the government, given this sort of monopolistic structure. And so the stakeholders here tend to be a combination of regulatory commissions or some governmental entities that are overseeing the operation, the entities that are operating the power grid, to just make sure that they're doing it in a way that's consistent with low cost, reliable, fair energy delivery. Then you actually have your power system operators who are responsible for managing, your power markets and making sure that those are fair and transparent. You have utilities who actually might own the literal, wires and infrastructure and manage those. And in some cases, system operators and utilities are separate, and in some cases, they're the same entities. So that varies based on where you are. And then you also have, in some regions, entities that are actually energy suppliers. They're actually selling you energy without actually managing any of the physical infrastructure. Other places where you have demand aggregators who are actually helping multiple entities manage their power more flexibly so they can participate in demand response programs. And then you also have consumers and quote unquote prosumers who are both producing electricity through, for example, rooftop solar, and also consuming electricity. So lots of different kinds of stakeholders on the system here. And there are some important considerations here also are that in different regions of the world, there are really different assumptions about, what power reliability looks like. So for example, in the US, there's an expectation that power will be available, abundant, reliable, 24 hours a day, 7 days a week, the entire year. Whereas in various other regions, like in India, there's some expectation and knowledge that there will be kind of power cuts in different times of the day. And so consumers are not necessarily assuming that power is always available, though hopefully and ideally that is changing over time such that kind of more people around the world have 24/7 reliable power. And then a kind of last regulatory consideration I'll bring up is something called a regulated rate of return. So this is so when a utility in many regions, how they actually get paid, because they're such a tightly regulated entity, is that if they invest money in something like, putting wires in the ground or building physical infrastructure, they're allowed to get some percentage of that back, basically as profit. But often when it comes to software upgrades or kind of the employment of AI on a system, that's not subject to a regulated rate of return. So utilities and system operators often cannot make money off of certain kinds of upgrades, even though they can make money off of others. And understanding these financial incentives that different entities on the system are facing is actually super important to understanding, what kinds of things different entities are incentivized to do and when. Like, are they incentivized to build physical infrastructure? Are they incentivized to deploy digital infrastructure? And can be a really important part of working with these entities to understand what the pathway to impact of your kind of innovation might be. So that's the overview of how electric power systems work. And so now for the rest of the time, we're actually going to dive into machine learning applications. So what I think I'll do is I'll start this section and then pause in the middle of it for the 5-minute break. And then we'll come back into it. All right. So for those of you who checked out the pre-readings ahead of this session, one of the pre-readings in there was a review paper talking about where machine learning can be used in sustainable energy systems. So this figure is from there. And to break it down, there are different ways that machine learning can be used to support the kind of mitigation and adaptation and sustainable development strategies we've talked about so far. One of them is providing situational awareness, so helping us understand what's actually going on in your power or energy system. The other is supporting centralized optimization and operation, so helping a centralized entity manage the overall system. We also talked about how the system is getting increasingly decentralized, and so there are ways that AI and machine learning play a role there as well. And there are also lots of ways that machine learning just helps make the system more efficient, reduces, breakages and wastages due to something being broken as well. In addition to literally operating a system, machine learning can assist us in helping us to plan what a future system might look like. There are also ways in which machine learning is being used to help us develop next generation clean technologies that will be employed on the grid. And kind of overarching all of that, machine learning is also used to help shape the policy and markets across these energy systems in ways that then contribute to these strategies. So I'm going to dive into each of these in turn. Starting with the use of machine learning for operations, which is sort of the bulk of this figure, because there's, of course, a lot going on in the operations space. So first, starting with situational awareness. So situational awareness means assessing the state of your power system in ways that allow you to then figure out how to operate it better. So this can include assessing the current state of the system. So what does my system look like right now? For example, what are the voltages on my power system? Often there are things like switches on power systems that are being turned on and off in ways that change what the actual topology or actual kind of connectedness of the grid looks like. So do we understand what our topology looks like? And also things like, predicting outages. We talked about security constrained optimal power flow earlier, trying to manage a grid in a way that is robust to various things being out, but you also want to maybe understand what is it exactly that is out about my system. In addition to understanding the current state, you also want to understand what the system might look like in the near future. So for example, what will my solar power production look like in the next 20 minutes, the next hour, the next few hours? What will my electricity demand look like? And what power generators are likely to be producing power? And as a result, what are the emissions intensities associated with that? that kind of prediction can help with strategies like demand response, because if you know that you will likely have a lot more low emissions power on the grid, then that might be a good time to shift some of the electricity demand too, so you can take advantage of the fact that there's low emissions power available. So when it comes to this sort of situational awareness applications, there are lots of different approaches that are taken. For example, forecasting is traditionally done through rule-based approaches, where you might actually just write down rules like, during a holiday, I expect electricity consumption to be higher or lower. During a weekend, during the afternoon, you actually just write down a bunch of rules and then use those to predict what your electricity consumption might look like. There are also physics-based approaches. So for the forecasting world, for example, there are things called numerical weather prediction models, which actually just write down what the physics of, for example, future sun, future wind might look like, and they use that to predict solar and wind power. Or also things like writing down something about the physics of your power network and using that to estimate what your current quantities look like based on some sensor input. There are also various, optimization approaches and statistical approaches in the fold, and then machine learning is also used to do both kind of state estimation and prediction of future state. So the pros here of using machine learning is that these methods are also often very fast. They're able to kind of make inferences from data very quickly. You can also throw in multiple types of data and allow machine learning to deal with all of those in a very powerful way, and I'll get to an example of that soon. And then also machine learning is very good at making near-term predictions in general. Often the situation an hour from now is very well described by the correlations and patterns in the data that I see right now. And so I can really powerfully extrapolate from the patterns I'm seeing right now to patterns I'm seeing in the near term. The challenge with machine learning is that you tend to need consistently formatted data. So for example, on a power distribution system, if you want to estimate what your voltages are now or in the next time period, then you need historical data ranging for a very long period of time in the past, that it's clean, that doesn't have too much missing, that looks very consistent. And you often don't have that. Whereas some optimization and physics-based approaches, they allow you to only look at a snapshot in time right now, use the data you have right now without expecting that the data is going to be perfect in the past as well. Machine learning also struggles with long-term trends sometimes, in the sense that it assumes that the patterns it sees in the data right now are the patterns that will exist forever. And if those patterns change, that's tricky. So for example, the economic situation changes, we might be in a recession, we might have a pandemic. So predicting electricity demand very long time from now might be subject to just completely different underlying economic patterns than it is today. And a machine learning algorithm wouldn't be able to pick up on that. And also, depending on the method, some machine learning algorithms are interpretable, but some are not. And so that's also a trade-off to think about depending on the situation. So an example here for where machine learning is used for situational awareness is electricity nowcasting. So the nonprofit Open Climate Fix worked with the power system operator National Grid ESO to improve both their electricity demand and solar supply forecasts using machine learning. On the demand side, what they did is the clever innovation was actually changing out the machine learning model. So they used a temporal fusion transformer on the existing data. And by doing this, they were able to reduce the error of both the 30-minute ahead and 2-day ahead forecasts by 2 to 3 times. On the solar power forecasts, what they did is they combined many different types of data. So they combined historical data on solar power production. They used satellite imagery and aerial imagery that was showing how clouds were moving overhead, which affects how much power your solar panel is going to produce. And they also used numerical weather prediction data, so data from physical models. And by allowing a machine learning model to cleverly learn the correlations and relationships between that data, they were able to reduce the error of their 2-hour ahead forecasts by about 3 times. So this is an example of machine learning being used for forecasting in power systems, which is probably one of the most common use cases deployed today for how machine learning is used in power systems. All right, so the next stage, so now that you know what's happening on the system, how do you actually operate your system? So when we operate our systems in a centralized way, you often have some kind of power system operator who is dispatching or kind of, directing how much power should be produced. So if you recall this AC optimal power flow problem I talked about before, that's sort of the centralized operation paradigm. The goal here is that by having better centralized operation, we can better integrate and plan for time-varying renewables. We can improve robustness against, for example, climate extremes. And we can also reduce waste by kind of allowing there to be fewer inefficiencies on the grid. But the challenge is to deal with that, we really need to increase the speed and scale and fidelity of existing optimization methods. Basically, as we have more time-varying renewables, we have to make decisions more and more frequently. As we have more distributed devices, there are just more devices to optimize over. And we have to increase the physical fidelity of our models because there's this concept called inertia on power grids, which basically talks about the amount of time we have to respond if something goes wrong. And basically, as we switch from kind of what are called synchronous power generators that actually have a spinning turbine providing some inertia to the grid towards things like solar and wind power that don't actually have like a spinning rotor, we actually lose some of our what's called, again, inertia on the grid, our ability to kind of have some buffer in our response. And as a result, we need our optimization models to be even more physically feasible than they used to be. And so the approaches that are here are used are traditional optimization approaches, both just trying to run your original problems and then also trying to run relaxed versions of those that maybe make it so that some of the physics mathematically is easier to deal with. And as a result, you can run the models more quickly. And there are also machine learning approaches. So some examples here are approaches to speed up the AC optimal power flow problem, doing things like looking at that optimization problem and classifying whether a particular constraint is likely to matter or not in that particular point in time. And if it doesn't matter, then taking it out so your optimization solver is dealing with a smaller problem. There's also some work that tries to predict quote unquote warm start points for the optimization problem. So trying to start your optimization solver in a better spot so it doesn't take as long to solve. And there are actually also approaches that fully try to approximate the AC optimal power flow problem using machine learning, often with some kind of feasibility constraining module in there to make sure that the answer that the machine learning model is spitting out makes sense. And again, you'll kind of in the tutorial, you'll kind of work with this area of work and get your feet wet in trying to actually speed up AC optimal power flow using machine learning. There's also some work using reinforcement learning approaches to actually try to switch various aspects of, switch the switches on the power grid, change how nodes are connected to each other, change how much power each power generator is producing in a little bit more of a kind of real-time way. And for those who are interested in this, I'd encourage you to check out the Learning to Run a Power Network Challenge, which is put together by RTE, the French system operator, as well as the Electric Power Research Institute in the US, that is trying to it provides a competition and a kind of simulation framework to allow you to try out the use of reinforcement learning on power grids in order to basically, see if you can come up with a better performing model for these purposes. All right, so moving on from centralized optimization, as I mentioned, the grid is becoming also increasingly distributed. So there are lots of devices like solar inverters and batteries and flexible consumers who can change when they consume power. And we want to try to manage these devices more effectively to, again, better integrate renewables, to also improve the robustness and reliability of the grid and reduce waste. So some of the same goals as centralized optimization. And what we need to enable this is control strategies that are really fast, again, that are flexible. They can adapt to what's going on the grid. They're scalable, so they can deal with the fact that there are tons of different devices. They're robust, so they don't break your grid. And again, physically feasible. They're respectful of the physics of the grid. So lots of requirements on these control strategies. And what's done in practice is a combination of control theory, so kind of more traditional approaches where you're writing down the mathematics of your system, as well as some kinds of guarantees you need to satisfy, and actually solving for a controller that will give you those properties. And then there are machine learning and reinforcement learning approaches that actually try to learn from data to figure out how to control your system. The cool thing about machine learning here is that we've started to see a lot of breakthroughs in other fields for reinforcement learning, where it's able to learn really, expressive and complex policies that are super well performing. So we've seen this, for example, in multiplayer online games where reinforcement learning is like beating humans very consistently. But the challenge is that machine learning methods are not often designed for kind of what are called safety critical systems where you have to make sure that you're not breaking the physical assumptions, that you're not breaking robustness, things like that. Machine learning approaches aren't necessarily optimized for that. They're optimized to do best in the average case rather than completely being airtight in the worst case. And so there's actually a lot of really cool work that's merging reinforcement learning and kind of data-driven approaches with robust control. So some work that's actually letting a trusted control theory approach and an untrusted machine learning approach both make recommendations, and then figuring out how to mix between the recommendations of those in order to provide some kind of controller. And then there's other work that is basically saying, let's actually write down control theoretic constraints and embed them into the design of a machine learning model. So you fundamentally have a model that is hybrid, that is both learning from data and is constrained in a way that's consistent with control theory, and is, as a result, kind of producing outputs that are safe. So I think this area of kind of, merging machine learning with existing types of knowledge like control theory is actually a really powerful paradigm for moving forward. And the last example I'll give before maybe entering into our break, or the last area I'll talk about, is, again, in this operations side of things, the area of predictive maintenance and efficiency improvement. So on power grids, you often want to, and in energy systems more broadly, you often want to detect inefficiencies or outages ahead of time or in real time in order to fix them as quick as possible, and as a result, reduce waste. The approaches that are used here are a combination of manually inspecting the grid, signal processing. So you take sensor information and try to just do some kind of anomaly detection or regular signal processing kinds of approaches on this, or also machine learning. The pros and cons here are similar to what I talked about on the situational awareness slide, so I'm not going to go into them again. But again, the idea that often near-term predictions are quite good, and that you can ingest lots of different types of data. But the challenge is that you often need a lot of consistently formatted data, which you might not have if you want to use machine learning. And some examples here include detecting methane leaks in natural gas infrastructure. So the figure on the slide is from a paper that actually released a data set that correlated, did some synthetic methane releases, and they then tracked kind of how much methane was released, and they tried to provide basically a data set for supervised learning approaches that might then try to predict methane leaks in natural gas infrastructure. There's also been a lot of work trying to detect anomalies or breakages in solar panels or in wind turbines or in batteries. And so the image on the slide is from a paper that's trying to basically take in various information about a battery in order to predict, how healthy the battery is, how long it still has in its remaining useful life, and things like that. And then there's also work that tries to detect what are called non-technical losses. So on power grids, you often have two types of ways that energy is kind of, wasted or dissipated. One is technical losses, which is just due to the attributes of how the infrastructure is set up. You're just going to lose some power as heat as you transport it. And then there's also non-technical losses where people are, tampering with their meters or stealing power or things like that. And so there's some work using machine learning to try to detect non-technical losses in particular in order to then deal with them. And these often combine between approaches that are writing down something about your power network, and kind of know how the power network works, and that are just learning directly from sensor data on the grid. So to give a bit of a preliminary recap, I know I covered a bunch of ground there. When it comes to the use of machine learning for power system operations, there are kind of 4 places where machine learning can play a lot of a role. So situational awareness, centralized optimization, distributed control and demand response, and predictive maintenance and energy efficiency improvement. And after the break, I'm going to dive into the last 3 pillars that are on here, which are planning, innovation, and policy and markets. So I'm going to pause us there. I think we have about 5 minutes allocated for the break. And of course, during that time, if anybody has questions they want to relay, feel free to do that. But also, of course, feel free to step away from the screen and take a bit of a break. And we'll be back in 5 minutes. And yeah, and Jorge, if there are any, Jorge or Samuel, if there are any questions that are coming up in the circle chat, feel free to relay them.
Okay.
Yeah, I think there was a question about this reference. Yeah.
Oh,
TK 2021.
yeah. So that is, and the slides will be posted afterwards, so you'll have access to all the references at the end. But that reference is to the article "Machine Learning for Sustainable Energy Systems," if you check the sort of pre-readings for today's lecture, that's one of the ones listed. So that's probably the easiest way to find it.
There is one interesting question. Do you want me to say it now, or?
Yeah, please go for it.
It says, what are your thoughts about the Jevons paradox problem? And then it explains, when increased efficiency enables further growth in our finite system and potentially generates more carbon emissions.
Yeah, that's a great question. I'm happy to start weighing in. And then Nsutezo, if you have thoughts on this question too, obviously, please feel free. So yeah, the Jevons paradox is something that's super important to think about. And basically the question is, if you make something more efficient, will it cause something to be used more? And if it does, to what extent is that use productive? Things to think about. So when it comes to kind of predictive maintenance, which I think is probably what when this question was generated on power grids, my impression is that when you're doing things like fixing electricity infrastructure to make it so that less power is wasted when transported along the lines, that in and of itself is not driving an increase in power usage. And so I tend to be a little less worried about the Jevons paradox there. So you're making the system more efficient, but not necessarily in a way that in and of itself will cause there to be additional usage. The other thing to think about, though, is that additional usage is not always a bad thing. Like if you're trying to, for example, grow a developing economy, you do want the ability for there to be more productive use of power because of various other objectives like sustainable development and things like that. So it's important to think about this both from a like raw emissions reduction perspective, but additionally from a, is the bounce back in use, is that productive for other reasons? And then to think about that as well.
Yeah, I agree with Priya's point. The only thing I was going to add there is also for emerging economies where resources are a bit more constrained, having benefits from energy efficiency actually help carry the resource a bit more and reduce wastage in that point. So not necessarily that it would lead to directly more consumption, which might not also be a bad thing, but these are also resource constraints economies that can benefit from energy efficiency in the system.
Awesome. There is another question that maybe we have a couple of minutes.
I think so. I think we have 2 more minutes left in the break. So absolutely, let's go for it.
Are there any unique characteristics that need to be considered when thinking about electricity systems in conflict areas?
Question. Yeah, I mean, I can start there. So I don't have honestly like a super informed answer to that. But there's been some recent news coverage of things like in Ukraine, how the power infrastructure has been a specific subject of attack, because obviously if you take down the power infrastructure, you're causing a lot of devastation to a place. And that the sort of Ukrainian power engineers, I think there have been some articles where they've just been doing, miraculous things that have continued to keep the system up that people didn't necessarily think were possible. So, yeah, so I think obviously in conflict areas, you also can't assume that your outages are going to be random on your grid. You have to assume that they're going to be targeted in certain ways, and that obviously changes how you manage the grid. But at least in the case of Ukraine, I think people are still trying to study and understand how exactly the grid is working as well as it is.
I think I could add as well that I guess the cyber layer that is being more important in the power systems field is also like something to think about, like, because there's been also like cyber attacks recently and everything's getting like more complicated, and yeah, something.
Yeah, there's been some interesting work looking at the relationship between cyber attacks and physical stresses on the power grid, in the sense that the power grid is often robust enough that it can deal with one thing. So if there's some extreme event for weather, it can often deal with it. If there's some cyber attack, it can deal with it. But if both things are happening at the same time, you're putting a huge amount of pressure on the grid. So there's some work about, for example, our cyber attacks being targeted on the grid specifically during times when the grid is going to face extreme weather for other reasons. And as a result, you have to be sort of double on alert for these kinds of things. So lots of really interesting and important kind of socio-political technical questions in there on how to keep the grid kind of efficient and decarbonized and running in a way that serves various objectives for people. Cool. So I think we are on minute 6 of the break. So I think actually maybe let's come back, and thanks everybody for the great questions in that interim period. So I want to kind of talk a bit more about an overview of a few more applications, and then we're going to kind of do some deep dives on applications after that as well. So first of all, planning. So far we've talked mostly about operations of kind of, you have an existing grid, how do you manage it? But of course, on power grids, we're often trying to, design or construct new components, or, reinforce existing infrastructure, or things like that. And so our goal here is to try to, build low carbon sources. We also want to try to strengthen connections between different power and energy infrastructure. So as Nsutezo mentioned towards the beginning of the lecture, one strategy for decarbonizing systems is to strengthen interconnections. So you can balance out variability between different systems, or exchange kind of energy types between different systems. And we also want to improve access to electricity and energy across a broader range of people. So the approaches that people use for planning power grids is a combination of physical simulation. So again, writing down physics or other equations and actually simulating those out. Multi-objective optimization. Again, manual surveying. A lot of power system planning is not just about the technical aspect of what should the grid look like, but also about getting permissions and buy-in from people whose land, for example, might be affected by this. And so there's a lot of work on just how do you build consensus and agreement among stakeholders who would be affected by planning processes. And then machine learning can often assist in the planning world. Machine learning is rarely the end-to-end solution to a planning problem, but it can provide some assistance in all of these things. So some examples here are in places where we don't have a perfectly accurate survey of where all the power lines are, or where all the solar and wind infrastructure is. Various approaches have used a combination of satellite imagery, aerial imagery, and graph search algorithms to try to provide a sense of where this infrastructure might be. There's also been work that's tried to provide assistance to these sort of physical simulation and multi-objective optimization approaches that are trying to plan things. And so the figure on the slide is from a paper that actually wrote down a multi-objective optimization problem for placing hydropower dams in the Amazon basin, with the idea that you're trying to balance between considerations like how much power is produced, but also the ecological health of the waterways in which you're putting the dams. So they wrote down a multi-objective optimization problem. This problem reflected what they wanted to reflect, but was computationally expensive to solve. And so they used actually not machine learning in that case. They used some, kind of linear programming and sort of pruning techniques to try to make that problem more tractable to solve. And then there's some work, including Nsutezo's own work, that has looked at predicting long-term demand for new customers of electricity. So thinking about if you're trying to expand or build grid infrastructure, you want to plan it to account not just for what you think the immediate demand for that power infrastructure is, but how that power demand might change, what productive uses might be enabled, and you want to sort of scope the infrastructure to be to be robust to that. And so past work has used a combination of survey data, of smart grid, of smart meter or meter information and satellite imagery to try to just better capture, are there signals in that data that tell us what the short and long-term demand for power might be in different regions and in different places. And as a result, can we actually create grid infrastructure that is going to continue to meet that projected demand right now? So in addition to planning grids based on kind of our existing technologies, we're often trying to innovate on new technologies in ways that we're trying to, develop new technologies to more effectively produce low carbon energy, or to improve energy storage, or to improve CO2 sequestration. And in all of these kinds of science and innovation scenarios, the main approach is that you have experiments that are often guided by humans in some way. So humans who are looking at past experiments, who are incorporating knowledge of the chemistry or the materials or what have you to develop these things. But then machine learning has helped provide some assistance to these human guided experiments to help humans kind of, operate, decide on experiments and synthesize things more effectively. So some examples are accelerated battery design. For example, there's a company that's basically using machine learning to analyze the outcomes of past experiments that are trying to design batteries. So those batteries might be for trading on power grids, they might be for electric transportation, but they basically are working with companies that are trying to create better batteries and analyzing their past experiments to see what patterns emerge and see if they can more effectively suggest which experiments to try next using physics-informed machine learning. And the company kind of reports that they've actually helped certain battery producers that they work with get a 10 times reduction in the number of experiments they actually have to run. And that's really huge because each experiment can take many months to run. And then based on the results of that experiment, you have to do the next one. So machine learning can help more intelligently guide the experimental process in these ways. Machine learning is also used in various ways to help with the experiments trying to create better nuclear fusion technologies. So right now, nuclear fusion is a technology that basically kind of mimics the process of energy production on the sun. And it is a technology that in principle could help actually provide abundant, clean, and reliable power, but in practice is still not at a stage where it's actually producing more power than it consumes, largely speaking, though there have been some recent breakthroughs or almost breakthroughs in that at the moment. But some of these technologies basically depend on superheating a plasma that goes through the fusion reactor, and this plasma can experience rapid instabilities that could potentially damage the reactor. And so machine learning has actually been used to predict disruption so that you can know when you need to shut down the reactor before the disruption damages the equipment. So there are ways like that. The machine learning is also just used as an inner loop to these broader innovation processes. Okay, last but not least, policy and markets. So we are, power systems are again, and power systems and are heavily regulated systems. They have both heavy policy kind of governing them. They also have markets that are operating within them. Innovation is often something that requires policy in order to help guide where we should make investments in innovation in order to kind of speed it along. And so it's obviously very important to have some input to the design and monitoring of policy, regulation, and markets. And there are lots of approaches that are used here. So for example, the field of policy analysis is a field that tries to just generally analyze kind of how good a particular policy is, what policy routes we should be taking, just try to provide input through a combination of techniques to the policy process. And then also market and mechanism design, which tries to basically just figure out what is the best market design that I can create. And these are supplemented by machine learning in many cases. So for example, there's some preliminary research work that tries to use reinforcement learning to set market prices in an energy system. So the paper that the figure is from here, what they're basically trying to do is have, if you have a distribution system operator that's coordinating with multiple different microgrids, those microgrids are sending information to the distribution system operator, and the distribution system operator is trying to figure out what price signals to send back in order to create the best kind of aggregate behavior across all of the microgrids. So there's been some work trying to use reinforcement learning in settings like this. There's some work that tries to guide the process of innovation by, for example, analyzing trends in solar power patents. So basically analyze past patents to understand what directions the innovations is going in, and that can potentially help guide investments to make sure that the sort of most promising areas of innovation are getting the resources they need to succeed. And then there's also some work that tries to help understand what the power system might look like in the future, in order to then guide, again, planning and policy around this. So the paper that's shown here, they basically are trying to take past information about demand or things like electric vehicle charging on power grids and use that to actually generate a bunch of scenarios for what potentially could power generation look like in the future, or power demand look like in the future. And then that way you can use that information to kind of come up with a synthetic data set of potential future scenarios in ways that allow you to kind of plan for, okay, if the system played out in any of these ways, how would it respond? And for these kinds of generative approaches on power system data, it's really important to make sure that you know what a good data set looks like. So if I generated future power system scenarios, how do I measure if this data set is realistic or actually capturing the structural factors that I needed to capture so that I'm actually planning my power system properly? Okay, so to recap, we went through a kind of big overview of machine learning applications in the power system, spanning operations, planning, innovation, and policy and markets. And next, we're going to dive into a case study, a bunch of case studies kind of trying to deep dive on how exactly machine learning might play out in a couple of these cases. But while we transition between speakers here, we wanted to kind of share a poll question with everybody. So what do you think are some important considerations to keep in mind when using machine learning for energy systems? Maybe thinking through some of the applications we just talked about and others that we didn't as well. So give everybody a few moments for that. And I'm also going to stop sharing Nsutezo so you can go for it after this.
So as Priya mentioned, we will be going through some selected case studies right now. Jorge, if any responses are coming in, please feel free to bring them up. This is the poll question again. What are some important considerations to keep in mind when using ML for energy systems?
Yeah, there's a couple. So data privacy, outlier detection and stability guarantees, that's one. Important to consider localization of data. So most energy data is US or European, and that does not apply like to other markets. The constraints, so making sure that you comply with the physical equations.
Yes.
Trustworthiness, net as well. Oh, sorry.
Yeah, those are really good constraints about the generalization of the work, the constraints of the system, and making sure that it obeys those constraints. And that's some of those are some of the thoughts that we want to be able to pull out from these case studies. We want to revisit this pathway, or this if I may say, flow chart of how to apply ML in the climate domain, but seeing how we can pull out some of these aspects from specific case studies. So again, revisiting this figure that was shown, I believe, at the beginning of the summer school, it's important to have a holistic view of how ML is going to interact with this specific domain, which is power and energy systems, considering how to best scope a problem, what are the tools, the data sets and methods that would help answer the questions at hand, what analysis are necessary. And this analysis could entail metrics, ML metrics, but it could also entail metrics that are relevant for decision makers or stakeholders. What is deployment going to look like once results are had, and considering ahead of time what some potential downstream effects in terms of equity, rebound effects may be. So we want to be able to take this framework and look at specific case studies and pull out some aspects, and hopefully that can provide a set of examples moving forward on how to think about ML applications in power systems. So the first case study that we're going to discuss would be mapping utility scale solar in India. And this case study aligns with some of what Priya had mentioned, which is along the planning line. But for some background, before we go to pathways to impact, India has a goal of 500 gigawatts of renewable energy capacity by 2030 and net zero by 2070. So in this particular work, the challenge that was being highlighted was the lack of accurate information about utility scale solar projects, where they are, potentially their sizes. And the objective there was to provide some insight as to the deployment of utility scale solar. Some possible approaches to answering that question could entail going to utilities at a very rudimentary level and getting information about what already has been deployed. It could be running surveys, looking at some open source data sets, or having some type of model that can detect utility scale solar from satellite imagery. And the choice of method that would be selected would be a combination of what's most valuable to answering the problem and what is most feasible given the data sets at hand. For pathway to impact, this work would be able to support information about where to build transmission infrastructure and how to best integrate it with the existing grid. It can help with monitoring progress towards the targets, for example, India's target of renewable energy capacity by 2030, and quantify the impact that renewable energy deployments might have on land use and potentially socioeconomic development if these projects are going to be deployed on lands that are already used for other things. So for this project, the stakeholders would be the energy planners who are interested in figuring out where best to place transmission, to support grid integration, policymakers who want to ensure that progress towards targets are being met, and communities who have a stake in the land, and also are potentially going to be end users of electricity once generated. From the ML standpoint, the data set that was used in this work was some points on solar PV farms, point labels on solar PV farms, coupled with Sentinel-2 data and some data sets on land cover and land use. And they took a two-step approach. One was a human-machine approach for weak label generation, where they were able to cluster some of the pixels given the point labels and get human feedback on whether those clustered pixels were attributable to solar PV panels, and in that way they were able to build up a weak label data set that they could then use downstream for semantic segmentation. Then from there, as I mentioned, they were able to build out their segmentation model using hard negative mining to improve detection of their panels. So in terms of the metrics, they had their ML relevant metrics, which are in this case mean intersection over union, precision recall, but also some other metrics that might be more relevant for decision makers. It could be the PV locations, which was the initial objective and size, the timing of deployment, the changes in land use and land cover. So the point here is that it's worthwhile differentiating between what metrics are relevant to evaluate the quality of the algorithm that's being deployed and what metrics are relevant to actually support action on the ground, given the objective of the work. The other thing that we want to be able to highlight is considering what the boundaries of any given methodology might be to understand how to appropriately extrapolate to new areas. So while the focus of this work was really about detecting the footprints, PV footprint, we need to be careful to not extrapolate too far out into other power metrics, for example, capacity factors, though this work was able to successfully achieve what they set out to do, which was detecting the footprints and validating it with installed capacity on ground. For deployment considerations, which comes into play when thinking about how to use this approach in new and unseen areas, I think someone in the poll highlighted this point is how well will this work generalize to new regions. So considering regional differences, different panel sizes, what is the sensitivity to different panel sizes, and how does one validate it in a new region that might not necessarily have the same type of data that was used in training the model. And then finally, what are some potential downstream effects of the work? It's worthwhile to consider what the implications of infrastructure detection, energy infrastructure detection might mean for that region. On one hand, it can support monitoring towards renewable energy targets, and there might be other downstream effects for consideration. Okay, so that's sort of the extent of this case study on how we are thinking about fully scoping or applying the framework to fully scope a project, evaluating the impacts beyond just the ML results. The other case study that we want to highlight is on downscaling solar irradiance from climate model projections. This work was focused on improving or getting higher resolution solar irradiance data through some super resolution techniques, which I'll go through right now. So in system planning, it's important to think about how climate change will affect renewable energy production, which sets the background for this work. And specifically, they observe that there's a lack of high resolution climate scenarios data that reflect how renewable energy production might change. And the reason is because global climate models are usually ran at coarser resolutions because of the computational intensity of these models. And as a result, the high resolution information that might be needed to understand how renewable energy production might change given these climate scenarios is not readily available. So they wanted to bridge that gap between both outputs. So some suite of possible ways, again, would have been to just use historical data or use generative approaches or finer grained climate models, but again, might run into some challenges such as the computational intensity of these models, or in their case, they apply statistical downscaling, which is an approach to provide higher resolution outputs, reanalysis outputs. The pathway to impact here is this would be useful for system planning, e.g. citing renewable energy, given how much you expect, and the stakeholders will be planners, policy analysts, utilities who are interested in low carbon renewable energy sources. So specifically what they leveraged to do this work were two data sets. One was the coarser resolution climate model outputs from, I think, Institut Pierre Simon Laplace, and the finer resolution reanalysis from ERA for solar irradiance. And the ML approach was to do a super resolution task, end-to-end deep learning model, where they did a residual dense block, or leveraged residual and residual dense block models and some subpixel convolutions to get good outputs. So they were able to start off with projections at a resolution of 1 degree and improve the resolution to about 1/4 degree. So the metrics here, they used a few metrics. One was a relative metric, which was the ratio of RMSE to the maximum, I believe, solar irradiance. And then they also included a structural similarity index measure between the climate model projection and the ground truth to make sure that there wasn't too much averaging in the outputs, which they observed when they just use RMSE alone. Some boundaries of this work are, again, back to generalization. This was a data-rich environment, but how well would it translate to areas where data is a bit more constrained or scarce, moving between past and future estimates, and also, again, taking into consideration the constraints that are, the grid constraints that are very readily present. For deployment or deployment considerations, if this work were to be generally applied, one question that stands out is, will the desired end user be able to access the data, discover it, and use it easily? So that's something that would need to be kept in mind if this is to be something that's deployed and leveraged for decision making. Finally, downstream effects, potential downstream effects might be the implications of insights accessibility to different stakeholders. How would they take this information and what would it be used for? We'll move on to the next case study. Priya, if you want to briefly go through this.
Yes, sounds great. And I'm there you go, sharing my screen. So yeah, all right. So we have two more case studies for you before we get on to sort of some wrap up and your questions. So the case studies talked about so far, or the last case study had to do with operations. So again, or sorry, with planning. And so this one has to do with operations. And so earlier I talked about this idea of using reinforcement learning to try to help manage power grids more effectively to try to help increase renewables and adapt to extremes. And the challenge is that existing power system optimization methods, as described before, are not sufficiently, dynamic or adaptive or robust or fast. And in addition, while there is some work trying to improve algorithms, in order to make those algorithms effective or really cognizant of the realities of your power grid, you also tend to need infrastructure like simulation to help, validate whether your methods make sense, to help guide the development of those methods in ways that are realistic with respect to the assumptions and realities of your power system or energy system. And ultimately, that can help you create this pathway to deployment such that if something works, then you can test it on a more advanced simulator and a more advanced simulator until you're sort of ready to potentially try to deploy it on your real system. And so from a methods perspective, different techniques have been tried, as talked about before, in terms of optimization, control theory, and data-driven methods like machine learning. And in terms of enabling infrastructure to help create these, test abilities to test and create these pathways to deployment, there's a need for simulators, test beds, and also at more advanced stages, quote unquote, digital twins that are trying to actually mirror digitally exactly what's happening on your system physically. And the pathway to impact for this kind of work is that your reinforcement learning methods for power grid management might be used by your power system operator, either autonomously, so the reinforcement learning algorithm might be fully controlling parts of the system, or in a quote unquote human in the loop manner, where the reinforcement learning algorithm is sort of working alongside people to manage the grid. This could be somewhat similar to the way we think about driving a car now. A human sort of steers the car, but there are a lot of automated processes underneath that are actually changing how the equipment interacts with each other in order to let the car be steered that way. So there's a lot of work that's thinking about how do you do something similar for power grids where you have a human basically steering the grid, but then something like reinforcement learning underneath that's actually trying to fulfill the directive from the human. And the stakeholders here are a combination of power system operators and also providers of power system software where these algorithms might actually be integrated. So the specific project at hand in this context is, as mentioned earlier, this challenge called Learning to Run a Power Network, run by RTE France, the Electric Power Research Institute, and various other academic and non-academic stakeholders. And what they do is they provide a simulator called Grid2Op that is actually a kind of reinforcement learning simulator for power grids. It's compatible with OpenAI Gym. So for those who have worked with reinforcement learning before, kind of a standardized way that you can create environments that are easy for reinforcement learning algorithms to work with. But actually, this is not limited to reinforcement learning. You can actually try out all sorts of algorithms and methods on these kinds of environments, but it just provides a really nice interface to be able to work with the inputs and outputs. In terms of data sets, they provide both topology and demand data sets, both synthetic ones, but then also ones that reflect more realistically the RTE system. And the machine learning approaches that have kind of, won through this challenge are a variety of reinforcement learning methods, some of which just use pure data, some of which combine that with heuristics about the system. So kinds of actions that the reinforcement learning algorithm should prioritize or ignore. And then also physical knowledge, so some of them that actually internalize information about the underlying power network in the reinforcement learning. The kinds of metrics that are used when evaluating these methods are the actual cost of power production. So how much did it actually cost to produce power? Physical robustness, so does the grid stay up when you use these kinds of methods? Speed, so are the methods operating fast enough to actually reflect what you would need to do in real-time operation? And these are really great metrics, but the sort of boundaries of the methodology here is that in general, the existing challenges are still reflecting, synthetic and smaller environments, and are still often testing the ability for reinforcement learning to be used autonomously rather than really testing out this human in the loop kind of paradigm where a human is then acting on these responses as well. When deploying these methods, it's important to think about the fact that, different power system operators have different, methods for actually, operating their system. So who the personnel are, how they interact with each other, how their systems operate with each other. And also similarly, some are more centralized, some are more decentralized, some are interfacing between centralized and decentralized modes of operation. So how do you deal with that? And there are also various downstream effects to think about. So if you use these kinds of algorithms, will it improve or will it make prices more or less expensive? Do people trust these algorithms? What are the implications for jobs in a situation where these algorithms would replace system operators versus augmenting system operators? If you have these centralized algorithms, how does that change the probability of switching to more decentralized market structures? And then also one thing to think about power system operations in general is if you're making power system operations more efficient, that can mean that you're paving the way to help, integrate more renewables, but it can also mean that you're just making current operations more effective, many of which are fueled by fossil fuels. And so these are just some downstream effects to be thinking about and measuring as you assess your application.
I will interrupt 1 second, Priya, because just to say that this competition is live now, like this year's competition of Learn to Run a Power Network is actually running like right now.
Amazing. Yes, exactly. So if you're excited about this, those who are attending, I definitely encourage you to check it out. Thanks, Jorge, for flagging that. All right. The last case study I want to bring up is one that actually falls a bit outside the taxonomy we talked about before. And this is actually machine learning to help work with power system data in order to help make that data more usable for those working in this area. So for example, there is data on, power generation, on the financial aspects, the physical aspects that exists among different sources. And often stitching that data together can be really useful for policymaking and climate advocacy. So you can understand for a particular power generator or set of plants, how did it operate? What were the financial implications? And just have that holistic picture from different data sets. The challenge is it's actually often hard to actually stitch this data together. So there might be the same power plant or power generator that's described in two different data sets, but there are no shared identifiers that tell you that those are actually the same power plant or generator. So the way this is often dealt with is you maybe manually go into the data sets. A human might know, okay, these two power plants are actually the same. But that's really hard to scale. There are also some heuristics where you can say if these two have similar-ish characteristics, they're probably the same power plant, but you can only do that to some extent. And then there's started to be some work trying to see are there machine learning-based approaches that can actually help to more automatically merge data sets. The pathway to impact here in this particular case is to release the data publicly. This is work done by an entity called the Catalyst Cooperative, and they work by kind of publicly releasing this data. And it's used for things like then estimating the costs of electricity and the emissions of electricity and which fossil fuel assets should most likely be retired, and enables these kinds of analyses. And these analyses are done by policy analysts, market designers, nonprofits. In terms of data set simulators and tools, they have two raw data sets that they're merging between FERC Form 1 and EIA, both data on power plants and power generators in the US. They take those raw data sets and they label them in a certain way that creates a machine learning data set. So the task they're doing is matching between FERC Form 1 and EIA data. So they actually do a kind of human labeling of the data set that tries to map some of the EIA data to the FERC Form 1 data so they can train a machine learning model. And then on that data set, they then use kind of logistic regression to try to identify matches between the EIA records and the FERC Form 1 data. So basically take their labeled data and see if they can find some patterns that they can extrapolate to the parts of the data they didn't label. The metrics that they look at are just sort of the accuracy of the data matches. So are the records that they are matching actually correctly being matched? And this is really powerful, I think, for US data sets, but the boundaries of the methodology are that the approaches are potentially very specific to these specific data sets in the US. So I think it remains to be seen kind of how generalizable this will be. And deployment considerations include thinking about who will actually use the data and how to make sure that they're, able and aware of this data to do so. And in terms of downstream effects, I think one kind of interesting and important thing that comes up is when you're making data more accessible, that improves accessibility for everyone, kind of regardless of what they want to do. So the same data that can be used to try to identify which fossil fuel generators should be retired can be used by a fossil fuel industry to know which fossil fuel generators are more likely to be retired and to therefore fight back against that. And so it's just something to think about when making data publicly accessible. How do you deal with this potential kind of dual use of the data? All right. So hopefully going through those use cases in a bit more detail highlighted the kinds of things that at least Nsutezo and I tend to think about when entering into a machine learning problem, really trying to think about the end-to-end, what is the problem that's actually being trying to solved? Why is it that machine learning is relevant, and what are the alternatives? What are the metrics we need to use to evaluate it, and what are the boundaries of that evaluation? Like, where is our evaluation limited, and what are the downstream effects that we need to think about there? And this ties into this broader discussion of important considerations to think about in machine learning and climate applications more broadly. So this is a slide you saw a version of earlier on, but kind of the importance of mitigating biases in your data and models, thinking about geographic disparities and modeling choices that might lead to different kinds of biases, the importance of trustworthiness and accountability, things like safety and robustness in power systems, and as well as interpretability, auditability, and human-in-the-loop approaches, which can be really important in policy-making contexts and in certain safety-critical parts of the power grid. The importance of centering equity and climate justice by working with a diverse set of stakeholders, by making sure that more people and more entities have access to capacity and compute, so that machine learning innovation is not just driven by a small set of people, and avoiding things like digital colonialism, where you're kind of extracting data from one place in order to create better algorithms that are then used to primarily benefit other people, which does happen with smart grid data, given that smart meter data has less privacy regulations in certain parts of the world than in others. So again, as sort of mentioned in the initial lecture, these kinds of considerations aren't exhaustive. It's super important to work with relevant stakeholders throughout the entire process of creating and scoping and developing and deploying and evaluating a machine learning algorithm in the power systems and broader climate context in order to make sure you're hitting these considerations. All right, so to wrap up, we want to talk about some next steps and opportunities for involvement. And so as part of that, both Nsutezo and I wanted to briefly share our journey into the machine learning and power system space. So Nsutezo, if you want to go for it.
Yeah, sure. You can just click to the next slide. I would say that for me, some of the very formative experiences I had is that I grew up and lived in a huge portion of sub-Saharan Africa, and those informed my views and perspectives, and specifically my interest in energy access and reliability. And going through my, if I may say, education, brought in the aspect of low carbon energy sources and how it can support sustainable development. My journey specifically has been through most recently Columbia University, where I got my PhD, and now working at Microsoft's AI for Good Research Lab, but also have been in other research labs and institutes, working with different organizations and utility stakeholders in Kenya, Uganda, and Rwanda. I'd say from my formative experiences and journey through power systems, some few things stand out, which I'd want to share now with you, Priya. I'd say find a topic and space that you care about. For me, like I mentioned, it was just informed by my experiences and what interests me. I'd say build knowledge and intuition through internships and best cases, and in the context that you would like to keep working on. Participate in competitions. Priya, Jorge have mentioned that we have the Learning to Run a Power Network competition going on, so feel free to partake in that. Most importantly, engage stakeholders, especially in the early stages of the project, to understand what's important for them and how they're going to use the outputs from your work. And then finally, just enjoy the process. I think sometimes it might come off as very serious, but I think at the end of the day, you should enjoy what you do.
Awesome. Thanks, Nsutezo. And for me, my journey into this space, so I knew that I wanted to work on climate change from a fairly early age. And then I fell in love with computer science, and I had no idea how those two worlds merged. And I was really lucky to both stumble upon this paper towards the end of my undergraduate journey called Putting the Smarts in the Smart Grid, which talked about how AI and machine learning would be critical to managing next generation renewable power grids. So I got super excited by that. And I also was lucky to find communities like the Computational Sustainability Network that brought together people who cared about computer science and sustainability objectives to share work and support each other through that journey. And I've had, really lucky to have a lot of really amazing experiences to help me further explore this. So I did something called a Watson Fellowship, where I got to travel for a year and interview people about power grids and sort of the technology and social aspects and policies behind them. Did my PhD at Carnegie Mellon, focused on machine learning for power grid optimization and control, supported by some internships at places like the National Renewable Energy Lab and National Grid ESO, where I got to better understand what the actual realities in the industry are, that kind of system operators transmission system operators and distribution system operators are facing. Gotten to collaborate with a bunch of great entities in this area as well. And then, of course, co-founded Climate Change AI during this time also. And I guess my top tips are, for those who are still students, taking classes in multiple disciplines is something really powerful that you can do. Problems in the climate and AI space are increasingly interdisciplinary. And so being able to really understand a problem from multiple perspectives and really stitch together those different disciplinary perspectives is super powerful. For those who are students or professionals, using internships or secondment programs to spend a short amount of time in a different kind of entity and actually lend your skills can be both hopefully great for that entity and a way to gain exposure to different pathways. Attending conferences for multiple communities, both virtually and in person, is a great way to understand what different people are thinking about and the problems faced in the field. Engaging with local organizations is also a great way to go. There are often, energy advocacy organizations or transportation advocacy organizations or various things in one's local community that you can tap into in order to become a part of that. Reaching out to people just on the internet using, for example, you can use the Climate Change AI community platform, directory, paper search tool to find people. Do your homework on what they're working on and what you'd like to do in terms of collaborating with them. But I think people are often really receptive to being reached out to. So there are, and these slides will be available afterwards. There's some further resources linked here where you can find additional, data sets and readings and collaborators and things like that. The kind of last poll of today, which we can kind of do concurrently to questions, is, given that we've shared a bit about what our journeys looked like, what will your next step be in your machine learning and climate and energy journey? We'd love to hear in addition to kind of, I guess, I know we're sort of close to the end of time, but fielding any additional questions that might arise. So thanks so much for your attention today.
Awesome. Thank you, Priya. Yeah, let's see if the responses come. There is a couple of questions already. I will start, and I'll also give the leadership to Sam in like 2 minutes because I have to catch a train, just so you know. One of them is, what's the state of data sets in ACOPF specifically? Like if there is some gap in the data sets or what is happening in the ACOPF field?
Yeah, it's a great question. So researchers from University of Colorado Boulder. So I know Kyrie Baker was part of this work. I unfortunately forget the name of the students who were, so apologies to the students, but they put out a data set called OPF Learn, which tries to just provide a kind of standardized way to generate data sets in this space so that different OPF algorithms can be compared against each other. I would say a gap that probably still remains, two gaps. One is that a lot of work on machine learning for optimal power flow assumes that the topology of your power grid is fixed from moment to moment, but in fact, your topology is changing. And so you need machine learning algorithms that can generalize over different topologies. But topology generation in power grids, or like generating synthetic power grid topologies, is a really hard thing to do. So I don't think any of the standardized data sets really capture a large and rich variety of lots and lots of topologies that you can train your machine learning model on. It's also the case that a lot of optimal power flow work is looking at, again, steady state dynamics of power grids. And there's a lot more work on kind of transient dynamics and dynamic stability that needs to be looked at. And some people are starting to come up with OPF formulations that deal with that. But since that's an early line of work, there then as a result aren't really benchmark data sets that deal with kind of transient stability and things like that.
Thank you, Priya. I'll leave it to you, Sam. I have to leave. But thanks a lot, Priya and Nsutezo.
Sure, thanks, Jorge. So let's take a look at some one more question before we look at the poll. So question here, how do you think stakeholders will integrate RL algorithms for operation? And how well do these models account for decentralized power, such as home solar, etc.?
Nsutezo, do you want to take this one?
So I think the first, if I can echo the question, you said, how would stakeholders take on these models?
Yeah.
I think the challenge there is, one, demonstrating the value and of the models, that one, they respect the constraints of the grid, and two, that they address the problems that the stakeholders are interested in, and three, that they can be easily integrated into their existing operations. So I think that's why we emphasize that prior to also building out the models, it's worthwhile engaging with stakeholders to understand what their current processes look like, what they're hoping to address, how it's performing, and what is an acceptable, if I may say, gain for them to be able to incorporate a model that does somewhat better into their existing systems.
Thanks. Okay, so we've got some responses to the poll here. Next steps in the ML climate journey. Building and launching a game-changing climate AI startup. Exploring exploring the problems in this area more deeper. Let's see what else. Someone here has a partnership with the national electricity supply company in South Africa to build mini grid technology. Sounds really cool. They're interested in load management, and this person thinks machine learning could have a big impact on how that impacts load management in these mini grids. A couple of people are saying it's quite these tutorials and the session has been challenging, but they've learned a lot, and I've given them some insights into this area. So grateful to the speakers.
Awesome.
And
oh, go ahead. And yeah, I'll weigh in.
yeah,
after.
I think that's pretty much summarized. Yeah, some of the response there.
Awesome. Well, really great to hear about those next steps and the journeys. And for those who are, like finding their way in this space, I would also encourage you to use the community platform to connect with kind of your fellow attendees here, to support each other and to connect with each other to onwards on those journeys, or to get feedback or advice. So definitely please do leverage that resource. And thanks for the kind words on the lecture. We definitely covered a lot of ground. We definitely did not expect that, any person will walk away having figured out 100% of the lecture, but we hope that the recording and the slides will allow you to kind of come back to the content and dive into different parts of it in the future as it becomes useful. And hopefully the overall lecture was helpful in getting at least an overview of the kinds of things to be thinking about in the area. So super appreciate the engagement through questions and through the polls and everything like that.
Yeah,
Awesome.
thanks everyone, and echo similar sentiments, and hopefully this serves as a launching pad into your own journey. Yeah.
Thank you, Priya and Simone, for your time for this excellent session and diving deep into power systems and machine learning and the opportunities, the challenges. Thank you all for your participation. As Priya mentioned, do make use of the platform to engage with the content and your peers and stay updated on this exciting field. Thank you all and have a good day.
Thank you. Bye.
Bye-bye.